So good morning, everyone. Let me begin my share screen. First thing I wanted to start with today is the GNU Radio Wiki, because I wanted to show that a couple of weeks ago and it wasn't working. So now it's working. If you go to wiki.gnuradio.org, or if you just Google for GNU Radio Wiki, you can get here. And there are two parts in the wiki which are very useful to learn about GNU Radio. One of them is this list of blogs, which you can go in here, and basically for almost all the blogs which are available in GNU Radio, there is good documentation for them. So, for example, I don't know, complex to real. Let's just pick that one. And this is a very simple math operation. So here it just says provides the real part of a complex stream, but you also get an example. For more complicated things, I don't know what I should pick. Maybe let's pick something like this one, FLL band edge. So you have some more involved explanation about what this does. This is some kind of, it's not a filter, it's something to recover frequency. So it's a closed loop kind of thing. But the thing I wanted to show is that for blocks that have parameters, there's also documentation about what each of the parameters mean, which of them can be adjusted at runtime. And then usually you get an example, and also in some cases the links to the source code files, which is sometimes useful to learn more about how the algorithm is exactly implemented. So very useful. And also in GNU Radio, I will show that later, there are links from each of the blogs to the blog page here in the wiki. So that's one of the main resources here. The other one is the tutorials. You can go in here, and they are categorized by difficulty and by topic. So if you are a beginner, you start here, and you can work your way through the different things which are in GNU Radio. And yeah, these are very useful. They go from essentially nothing to building completely functional radio receivers and transmitters. Like, for example, if you go here into packet communications, it tells you how to build a complete radio which is sending data packets. And here you have like the code, all the examples. So yeah, great documentation. And this is continuously improving. So there are people working on this all the time. Then what's next? So for today, I have two things. The first one is this IQ sampling thing. The goal of it is to explain to you why we use complex data in digital signal processing. So it's called IQ for in-phase quadrature, or it's called complex sampling. So why is that useful? That's the goal of this tutorial. And then the second one we will do today is this spectral analysis, which has multiple goals. The first is to learn how to generate some basic signal types, and this can be used, I don't know, for simulations. You could use them as a SETI, as an ETA candidate kind of thing. So you could be trying to see, can I detect this signal if it's weak and if it has Doppler or something like that. So signal generation of some basic signal types. Then also how to uh, measure the spectrum of those signals, which can be very easy, but it can also lend to more complex things. And finally, what are some of the important parameters in that spectrum processing that determine how sensitive we are? So how easy it is to detect these different signal types if they are weak, and also how some of the parameters play a factor in here. For example, there is something called the FFT window, which can be chosen to optimize for some characteristics or some others, depending on exactly what we need to do. Yeah, so there's a whole lot of stuff in here. Some of it is pretty basic. Some of it it's already going into more advanced things. But let's get started with the IQ sampling. So for the IQ sampling, I'm actually going to cheat a little bit. And because all the blocks that are used in here, we already used in the previous tutorial. And there are a bunch of them. So you can see it's like this big because I want to go step by step, showing different examples. I don't want to explain this to, I don't want to put this like completely from scratch. So I have this, which is the same, which is on the GitHub. And I'm going to be going step by step, enabling and disabling blocks. And this will save us some time. So to start, I'm going to do something really, really simple, which will set the stage. And this is actually nothing new. I'm going to generate a cosine waveform, and this is going to be real. Uh, it is set here to output type floating, so it's a real cosine function. And we can see it here. It's just a cosine function. The frequency is 1000 hertz. In here, we have 10 milliseconds, or there are 10 periods of this cosine wave. Nothing very surprising, but the important thing is here. So this is the frequency sink I have in here, and this is showing the spectrum of this signal. And if you know something about Fourier analysis, you might remember that if we have a pure signal, like a pure tone at a given frequency, in this case 1 kilohertz, we expect to see a peak on the Fourier transform, which is the spectrum, so a peak in the spectrum at the frequency of that signal. And if I zoom in here, we can see that at 1 kilohertz, there is a peak, which means there is only power at 1 kilohertz. And the rest is basically zero. If I zoom out a lot, we can see all this noise, which is basically due to errors in floating point calculation. So this is never going to be an exact sine wave because of floating point precision. But that's it. But the important thing here is, why is there a negative frequency? And we will keep exploring this concept, but right now the point I want to make is that physically it doesn't make sense to speak about negative frequencies for a wave like this, because the frequency is the number of oscillations that the wave makes in 1 second. So here we can say it makes 1,000 oscillations per second. It doesn't make sense to speak about this wave makes minus 1,000 oscillations per second. So it should be a non-zero. It should be a positive quantity, right? In physical terms. So the thing which is going on here, at this stage, we could say, well, so the FFT is this mathematical operation, and it actually involves complex numbers. If you have seen the definition, there is like a complex exponential there always. So because of the way it's defined, and this is just like a mathematical artifact that happens because of the definition, if you compute the Fourier transform of a real signal, the output you are getting has this symmetry, and at each negative frequency, the value you get is the complex conjugate of the one at the corresponding positive frequency. So it has this symmetry property, and so we can think about the negative half of the spectrum, but it's actually mirrored. So it doesn't add any new information. And so that matches our physical intuition, because this is like this mirror thing that appears just because the mathematics require it. So at some point, at this point, nothing too complicated, and the complex number have only entered the picture because we want to compute an FFT, because we want to show the spectrum of the signal. Any questions about this? Okay, excellent. So now to motivate the rest, what I'm going to want to do is to shift this signal in frequency. It is currently at 100 kilohertz, and for the sake of the example, I could also set it at a much larger frequency. I normally don't do that because then here it doesn't seem like a sinusoid anymore, and it actually is. It's really not a sinusoid because uh, there are so many data points. We are doing discrete time sampling. So if you have too few data points for each cycle, then it looks like this thing, which is only approximately a sinusoid. But anyway, and here we can see our signal, and let's think that we want to move this to zero. You will have to bear with me that this is a useful operation to do in signal processing. It kind of centers things, right? So if I want to work on the signal, it's better to put it at zero, which is like the center. And then, for example, if I want to filter the signal, I can use a low pass filter. We will see those in another week, which selects this part of the spectrum. And it is way easier to work with low pass filters than to work with a band pass filter, which would be placed here. So you need to believe me that shifting things in frequency is a useful operation to do in signal processing. Another example I can give is Doppler correction. So you might already have learned that because things move in space, or it doesn't have to be space, it can also be terrestrial radio stations, emitters and receivers. Because things move, there is a Doppler effect that shifts things in frequency. And that's inconvenient because if you have a system, it's prepared to work with signals at a given nominal frequency. If things have been shifted in frequency because of this Doppler effect, we need to correct it. We need to apply the opposite frequency shift. So that's another example of why shifting signals in frequency is useful. And essentially, it's like panning for images. In images, you can imagine that moving things can be useful, right? So in signals, the frequency domain is quite important. So moving things around in the frequency domain is an important operation. Okay, so this said, how can we shift our signal in frequency? Well, there's a way to do it, which is to multiply it by another sinusoid function like this. And that's my second example. So for that example, I'm just going to enable these blocks. I need here now 3 inputs again. And then I'm supposed to connect the multiplication to the last one and this one here. So the thing we have now is two sinusoids. They have different frequencies. By default, they are both set to the same frequency. But this one uses this frequency QT entry thing, and this one uses the LO frequency, and LO means local oscillator. I will explain in a second why that is usually called local oscillator. So this is the local oscillator frequency, is the frequency of the second thing. Yeah, I'm saying something dumb. I was looking at this 100 kilohertz, but this is the sample rate. So they are actually set at different frequencies by default. This signal source is set at 1 kilohertz, which comes from here. And this signal source is set at 0 hertz, which comes from here. And because these are GUI entries, we will be able to change each of them independently. So we have these things of different frequencies, and we plot each of them, we multiply them and plot the result of the multiplication. So let's see how that works. I'm going to zoom in here to show you things better. So far, this local oscillator is set at a frequency of 0. That gives me just 1 as an output. You can see this local oscillator is the red thing because the cosine of 0 is 1. That's what I get. So far, I'm doing nothing. I'm multiplying my input signal, which is the blue thing, by just 1. So then the product, which is this green thing that is overlapping, is exactly the same as the input. And here we get what we expected. A constant 1 has a frequency of 0, so we only see something here for the local oscillator, is the red thing, and then the input signal and product have tones at 1 kilohertz and minus 1 kilohertz as before. So far, nothing surprising. But then, for example, let's see what happens if I put 200 hertz here. Then my local oscillator looks like this. So it does a couple of, actually two cycles on this plot. And then the product is this green thing. So you could imagine, right? You are multiplying the blue thing and the red thing. So when the red thing is large, you get this green thing is almost the same as the blue thing. Now this is decreasing, so the product is decreasing. Now this is negative, so the product has opposite sign from the blue thing, and so it works out. So it has this shape. And then the question is, how does this shape actually look like in the spectrum? And we see that there are these four peaks. So we have 800 hertz, 1200 hertz, and then the negative equivalence of this, which we always get because of how the Fourier transform works. So the question is why we get 800 and 1200, and you can notice that these are 1 kilohertz plus 200, which is this 200 frequency, and 1 kilohertz minus 200. And the reason for this is, well, there is a maths formula about trigonometric identities. If you happen to remember any of that, the product of two cosines is equal to the sum of, I don't remember if they are cosines or sines or anyway, sinusoids of the sum of frequencies, and one is the sum of frequencies and the other one is the difference of frequencies. So that is the reason why we get the sum of frequencies and the difference of frequencies. Essentially, there is a maths formula that tells us that this is what happens. So that's one way of understanding this result. And then why is this useful to us? Because what we wanted to do is to shift this thing in frequency. Well, we have kind of shifted it because, for example, we have this one. It's like a shifted copy of this thing. We also have this one, and we only wanted to shift a single copy, but maybe there's a way in which we can make use of this. And if we, for example, increase the value of this, as you can see, then it's further spaced out. So we get 400 because it's 1 kilohertz um, minus 400, minus 600, sorry, and then 1600, so 1 kilohertz plus 1600 hertz. And if I continue playing this game and I set this at 1000, then what I get is the signal has moved at 0 hertz, which is kind of what I wanted. But now I also have this other thing at 2 kilohertz. So this is unwanted. This is the wanted signal. There's a way to get rid of the unwanted signal, so it's not a huge problem for us. We could apply a filter that only lets this signal pass through, and it will remove this signal. So in this way, we can perform this multiplication and do a frequency translation. So shift things in frequency by multiplying by another sinusoid. And this works for any kind of input signal. Here I have a sinusoid for simplicity, but we could generate other signals and we would see that a copy of the signal is shifted here and a copy of the signal is shifted there. So that's what happens. Another way of understanding this effect, and let me, for example, do that with 800 here. It's better for the example, is that the reason why we get these four peaks at these locations is because we are going to get a combination of all the pairs we can make on the spectrum. So what happens is this thing will shift the signal 800 kilohertz up. It's a convolution. If you have heard anything about convolution, then you might recognize this as a convolution. If you are not familiar with convolution, you can just forget about that I said convolution because it confuses more than it helps. So this thing shifts the blue thing by 800 hertz, and so we get this signal and this one. And because there is also this blue signal here, when we shift it up, so to recap, we have this blue signal. We have these two blue signals, and when they are shifted up by 800 hertz, which is what this red signal does, we end up with this and this. But then there is also this red signal. And what this does is to shift things 800 hertz to the left in frequency. So then these blue things become this one and this one. And this is the reason why we get four distinct peaks in the spectrum, because there were initially two in the input signal, and we are shifting them in two opposite directions. So that's another way of thinking about this operation. Um, any questions so far? Okay. Then the next step would be to say, well, yes, this works. It kind of works with real sinusoids, but we get these extra peaks that we don't want, essentially because there are things at negative frequencies. How could we work with that? Is there a way to avoid it? And yes, there is. And that's the next example. So let's try to do the same but with complex signals. And the first thing I want to show is actually this little thing. So I'm generating a complex exponential. This is just the cosine is on the real part, the sine is on the imaginary part. That's the definition of the complex exponential. Uh, and then what I'm going to do is I'm going to plot it on the complex plane, which in GNU Radio is this constellation sync. It's called constellation sync because for digital communication signals, we use the complex plane to encode data, and the different ways in which we can encode data are called constellations. So that's why it's called constellation sync, and because it has a funny name, maybe this is a good chance to go and visit the documentation page. So I just right-click it on the blog, went into documentation, and there is this link which will get me directly into the documentation about this. And there is an example. And this is a digital communication signal. So you can see there are points here, there are points here. This is the way that a binary 0 is sent by the transmitter. This is the way that the binary 1 is sent by by the transmitter. So this is a very simple encoding. You could imagine that another radio modulation could have more points wherever you want to put them, and they would encode more complex values, essentially multiple bits per point I have on the constellation diagram. So so far, what I want to do is I'm going to plot on the complex plane this sinusoid, and I'm going to plot separately the real and imaginary parts. The way to divide a signal into the real and imaginary parts is with this complex to float block. It will give me the real part and the imaginary part. And then because this block requires complex inputs, I'm converting each of them to complex by putting the value, well, actually, I'm putting the value in the right place. So the real goes to the real, and I'm putting zeros. This null source is generating zeros. You can either use null source, or there is another block which is called constant source, and you can set it to 0. So you could use either of these. They do the same. So the real goes into the real, and I'm putting zeros in the imaginary part. And for the other one, the imaginary part goes to the imaginary part. I'm putting zeros in the real. So it might be slightly confusing. You will see what I'm doing when I show you this thing. So basically, I have my complex exponential, and it's going around in a circle like this 1,000 times per second. If I look at the real part, it's going back and forth like a sinusoid, like this, 1,000 times per second. If I look at the imaginary part, it's going up and down like this, 1,000 times per second. Because this is 1,000 times per second, it's like running around very fast, and it's impossible to see it. If I set it to a frequency of 0.2 hertz, that means that it takes 5 seconds to do a lap around the circle, and you can see it more clearly, right? You can see the blue point is going around the circle, And then the red and green are basically the real part and imaginary part of that point. They are the projections on the axis. And I'm showing this, which it doesn't seem to have much to do with signal processing, because it's a very neat example to motivate negative frequencies. So what you can see here is that this blue thing is rotating counterclockwise. It's going in this direction, right? And that's the way that the complex exponential is defined. If I put a minus sign in here, then something interesting happens, which is that basically everything is reversed. And now the blue thing is going in the opposite direction and it's rotating clockwise. So the point I want to make clear with this example is that for a two-dimensional thing which is rotating, like this complex number, it makes sense to distinguish positive frequencies and negative frequencies because they can encode the direction in which we are rotating. By convention, positive frequencies mean we are rotating counterclockwise, and negative frequencies mean that we are rotating clockwise, as in this case. However, if we look back at each of the green and red things separately, we can no longer see any difference. For example, the red thing is going left to right and then right to left, and it's impossible to tell whether the thing is supposed to have a negative frequency or positive frequency. We can see this is a negative frequency, it goes left to right and right to left. I can change the sign of the frequency and it also goes left to right and right to left. So I think this is a good explanation about why, if we want to work with the concept of negative frequencies, then real signals don't actually have them. They cannot distinguish between negative and positive frequencies, but complex signals do, because they have real and imaginary parts and they can be rotating in one direction or the other one. Uh, Questions about this example? Okay, so the next thing I'm going to do is I'm going to keep this and I'm going to show you the same thing. It's basically how would this example, which is two sinusoids, we are multiplying them and showing them in the frequency domain and in the time domain. How would that look like for complex sinusoids? This is the example. Let me actually disable this one because we don't need it anymore, I think. So let's go step by step. I can disable all of these and keep just the input signal. So for the input signal, we have a real part and we have an imaginary part. And we can see they are both sinusoids. The blue is supposed to be the cosine, which is the real part. The red is supposed to be the sine. Something you can notice is the blue comes before the red. There is a sentence that you can use to remember this, which is I leads Q. I comes before Q. And that is the case when the frequency is positive. Here, the frequency of this thing is 1000 hertz. This is what, when you plot these things in the complex plane, not just versus time, makes the function rotate counterclockwise. If I change this to a negative frequency, so minus 1000, you can see that the order of these things is swapped. Now the red comes before the blue. So this is a negative frequency. That is also a reason why we can distinguish positive and negative frequencies, because we have two components, real and imaginary, and one of them needs to come before the other one. So that's the difference. Now in the Fourier transform, what we can notice is that we only get one single spike at the positive frequency. So we get 1 kilohertz, and there is nothing at minus 1 kilohertz. Conversely, if I set the frequency at minus 1 kilohertz, then there is a tone at minus 1 kilohertz. There is nothing at plus 1 kilohertz. So complex exponentials like these really are the objects we need to work with if we want to distinguish positive and negative frequencies, and if we want to get Fourier transforms which are not mirrored, which have information both in the positive half of the frequency spectrum and the negative half of the frequency spectrum. And because of this property, it is so much easier to work with complex exponentials. So now you can see I have my local oscillator. It's still at 0, so that's not interesting. As before, it's multiplication by 1. But if I put it at 200 hertz, the same as before, we can see the green, which is the real part, is leading the red, which is the imaginary part. And I can enable this in the spectrum, and I can see there is only a single thing at 200 hertz. So that's great. Then how does the product look like? Well, the product is this thing. It is now slightly more tricky to see things here. You need to look at these cyan and magenta traces. You might be able to notice that they actually look like a sinusoid function or sinusoid functions. Again, the blue, which is the cyan, sorry, which is the real part, leads the magenta, which is the imaginary part. So that tells us that we get something which is a positive frequency. If you remember anything about complex exponentials, this is just multiplication of two complex exponentials. And because the frequencies are on the exponent, what happens when you multiply is the exponents are added together, so we get the sum of frequencies. So hopefully the thing we are getting in here should be sinusoids at 1200 hertz. And if I show this on the frequency domain, that's exactly what we get, a 1200 hertz tone. So this is much more convenient than operating with real sines and cosines. We only get a single signal for each of the signals, or I should say a single tone for each of the signals. And so what we get as the output is the sum of these two frequencies. So it's much easier to work with this. Questions here? Okay, so if I want to shift my blue signal back to 0, the thing I need to do now, it's pretty clear. I need to set this to minus 1000. And this thing is my local oscillator at minus 1000. At the output, I get the difference of frequencies, which is 0. And so at the output, it is this cyan thing and this magenta thing. I get a constant, but the constant is a complex number. And so it has a phase or an angle, which is like the arctangent of the imaginary part divided by the real part. It doesn't really matter. Complex numbers have an angle, and the angle tells us about the phase relationship or difference between the input signal and this local oscillator. So this is a nice way to work with signals. It gives us the ability to shift things easily in frequency, and it's how many or most radio receivers actually work. Even physical receivers like the RTL SDR stick you have, there are some electronics in there doing operations which are similar to this. The signal which arrives at the antenna on the RTL SDR, it's definitely going to be a real signal because it's a physical quantity. It's going to be a voltage. So that's like a single real number, which changes over time. But then there is a reference sinusoid, which is generated by the electronics inside the radio receiver, which is this local oscillator. And this is the reason why this is called local oscillator. So this is something that was invented very early on when people were designing radio receivers. We have an oscillator which is local. That means it is in the radio we have here. So it's local to my RTL-SDR stick. It's not on the transmitter we are trying to receive. It's on the radio we have here, right? So it's this reference oscillator that we have locally that we use to mix. It's called mixing in analog electronics, to mix the incoming radio frequency wave and shift it in frequency so that so that it's easier to process. For example, it can be easier to filter things in the analog domain when there are at a certain frequency. It might be easier to design filters for that frequency. It might be easier to sample them and convert them to digital values we can use in the computer, and that's also what happens on the RTL-SDR stick. It might be receiving an RF frequency which is pretty high. The last session we were playing with signals around 100 megahertz, which were broadband FM radio stations. But the thing is, the ADC, the analog to digital converter, which is inside the radio, works only at a few megasamples per second. So that means that to digitize those radio frequency signals, first we need them to convert them to much lower frequencies, essentially to move the signals of interest pretty close to zero so that we can sample them and convert them to digital values. That's how mostly every radio receiver works. So this is very useful, not only like in mathematics in the computer, when we are doing digital signal processing, also in actual electronics, in the hardware part of all the radio receivers. Any radio receiver needs to have some hardware portion to it. You cannot just put radio frequency voltage directly into the computer and do something with it, right? Okay, questions about this example? Great. Then what's next? Well, there is a minor comment next, which is, so if you remember here, to move this signal to zero, I need to set the opposite frequency from the frequency of the signal. So if my signal of interest is at 1000, to tune to the signal of interest, I need to put minus 1000 in my local oscillator. That can be inconvenient because you need to remember to put the minus sign. So there's a way to get around that, which is to use the multiply conjugate operation. That essentially flips the frequency of the second term. So if I use this like so, then what you can see is that now what I get is what happened. Oh no, that's correct. Yeah, it's more difficult to see because things are on top of each other. But I will show you. So if I set this to minus 1000 as before, then this is at 1000. My local oscillator is at minus 1000. And then because I have this complex conjugate operation, I get something at the difference of frequencies, which is 2000. If I want to have this green at zero, then the number I need to use in here is 1000, which is easier to remember. It's like I want to tune to 1000, I just put 1000 here. And then things are on top of each other. So basically the blue and the red are on the same place. And now the green is at zero. So just the remark that you will often see this multiply conjugate operation because it actually computes the difference of frequencies. This one computes the sum of frequencies. And the second remark is this multiply conjugate is nothing else than doing a complex conjugate operation on the second term and then a multiply operation. So you could also see this multiply conjugate being performed like that. That's the only remark there. And then finally, the last example I have here is how do we combine these things? We have seen one example here with real signals. The next example was with complex signals. How do we work if we have a real signal to begin with, which, for example, it's what happens with the RTL-SDR stick. The signal in your antenna is real, it's a real voltage, but then you might want to work with complex signals and have a complex local oscillator. So how can we do that? And there are two ways of doing that. I'm going to show the easiest way first. So what we can do always is, well, this real function can be thought of as a complex function. We can just convert it to a complex number by putting the values on the real part and putting zeros on the imaginary part. And then how does that look like? So in the frequency domain, we can see, I'm going to disable the product for now. We can see the input signal is, as earlier, a cosine function. It has frequency components at plus 1 kilohertz, minus 1 kilohertz. And then at the moment, my local oscillator is just here at 0. So the product is the same as the input. If I set this to, I don't know, 200 as earlier, then what happens is these two blue signals are shifted up by 200. So if what I want to do is to shift this one down to 0, then I can use minus 1000 in here. And what happens is my local oscillator is as minus 1000 as before, but now because my input is real, this thing, which is the positive component, goes to 0. And this thing, which is the negative component, remains. It's now at minus 2 kilohertz. And this is an unwanted output. We want to get rid of it. So as before, what we can do is apply a filter. We can, as I mentioned before, we can apply a filter. We will learn how to build filters in another tutorial, and the filter will only let this signal go through. And this is actually how the RTL-SDR works. The signals from the antenna would be the blue thing in here. The red thing is that local oscillator, which is generated on the receiver. There are actually two local oscillators, right? One is playing the role of the real part. The other one is playing the role of the imaginary part. You cannot have physically complex voltages in a circuit. You can only have like two different voltages on two different copper paths, and that is what happened. That is what is happening physically inside the receiver, but conceptually, it is a complex local oscillator. And then because there is a complex local oscillator, we get this unwanted signal, but we remove it with a filter. And then we only sample with the analog to digital converter this signal. And that is how many receivers work, not only this RTL-SDR. Okay, questions at this point? Okay, and finally, to wrap this up, if we are already working with digital signals here, like in GNU radio, there is something very simple we can do to convert real signals to complex. It is called this Hilbert filter. And I'm going to show you just so that you know it exists. Might be useful at some point for you eventually. And what this does, I'm going to show mainly the blue signal, which is the input. We are running the input signal through a Hilbert filter. So the Hilbert filter, the intention is to remove all the negative frequency components. Here we are seeing that it's not doing a great job because this is the positive frequency component. It has some amplitude to it, I don't know, minus 10 dB. Then this is the negative frequency component. It has some other amplitude to it, so minus 20 dB. This Hilbert filter has managed to remove some power from this thing, but it's still remaining and it's still fairly strong. But the reason for that is the frequency of the signal is pretty low. If we increase the frequency of the signal, we can see that the Hilbert filter makes a better job. So now the component which is at positive frequency, it's still again at about minus 10 dB. The negative component is at minus 78 dB pretty much. So this is a really tiny signal. We can only see it here because there is no noise. Everything is like an ideal simulation. If we were to have noise, the noise floor would be like over here, for example, and this thing would be buried in the noise. So effectively, this filter has managed to remove the negative frequency component from the real input signal. That's what the Hilbert filter does. It removes all the negative frequencies. It works less well for frequencies which are close to zero, but that's what it does. And if you ever need it to work better at frequencies close to zero, you can always increase the number of taps, which is how many operations this filter is doing. For example, let's do 650. And you can see now that even with the original thing at 1 kilohertz, it does a much better job at removing this negative frequency. Uh, so this is a tool that is used within signal processing to convert from real signals to complex signals by discarding the negative frequencies. Uh, Questions about this operation or about any of these in general, because the next thing we will do is somewhat different. It's the spectral analysis tutorial. Okay, so let's move to the second tutorial. This one I'm going to make from scratch, and as usual, we will take a break more or less at the top of the hour. So I will just get started and see where I can get before the break. So spectral analysis and the sample rate is going to be 1 megasample per second, which gives me a bandwidth of 1 megahertz. And I'm going to save it here like spectral analysis 2 to avoid overwriting the original. And let's begin with something really, really simple. So we know already that to display signals in the frequency domain, we can use this frequency sink. A very basic signal is noise. And we have seen that real world receivers have always some noise floor. There is noise in the electronics, there is noise in the environment in which the antenna is. Having some noise is inevitable. So it is important to know how to generate noise. And that will be my first example. It's just generating noise. So as usual, when we are doing simulations and there is no hardware involved in the simulation, we need a throttle block to limit the rate at which samples flow through the flow graph. So here we have noise, and it's not very interesting by itself. We can apply some FFT average if we want to measure the level of the noise more accurately. But what we can notice at the moment is, well, this is random. This looks pretty much like the noise we saw on the RTL SDR receiver, especially if there is nothing connected to the antenna. And that is because this is Gaussian noise, which is the noise we typically find in radio frequency. And also something else we can observe is that this is flat on the spectrum. So there is the same noise power on all the frequencies that we are simulating. And the term we use to denote that is white. White, it means that it is spectrally flat. This noise source can be used to generate Gaussian noise. It can also generate other types of noise, but to be honest with you, the other kinds of noise are used very infrequently in signal processing. So Gaussian noise, so far so good. Another signal type that we already know how to generate is a narrowband signal. That is a signal which occupies a single frequency. We know how to build that. We can use the signal source, and I'm going to pull this down. We can use this cosine, and basically if I want to have the two of them, I can add them. And by doing so, I generate something which is a combination of the noise, which is intended to represent the noise floor of my receiver, plus the signal, which might be something that something is transmitting. And we can see what is the error port not connected. Which port? Out is not connected in zero. Have I dragged two different add blocks? I cannot see it. Yeah, I think there might be. Yeah, sorry. Somehow I managed to put another add block into the flow graph, like far away. But this should be correct now, and now it can run. So nothing too special. We have this thing at 1 kilohertz, and then there is the noise floor. So pretty much what you imagined. Here, someone might ask, does it matter to put the throttle block here, like on just one of the signals, or here? Do I need a second throttle block here if I put it like this? And the answer is no. You should only have one throttle block, so don't put a throttle block here. And also, you can either put it here or there. And the reason for that is the throttle block is limiting the rate at which samples flow through here. You can think of this like a valve, but then add is going to get one sample from here, one sample from here, and send it to the output. So this is not going to run faster than this because it is limited by the addition, because we need to pair samples up. These ones are already limited at 1 megasample per second, so these will get limited because of the addition. So you can put the throttle block pretty much anywhere you want to in one of the sources you have. You can put it next to one of the outputs. You can put it where you have combined everything. It doesn't really matter. Uh, okay, so we want to do something slightly more sophisticated with this signal, which is we want to be able to control both its frequency and its power. And if this works, I'm going to copy and paste. No, it doesn't. Well, I'm actually going to do it like this. So to save me some typing, I'm going to, I don't want to go and type tone frequency, set default values, but this is a QTQ entry to set the tone frequency. So in this way, we can edit the frequency. However, when we speak about power of the signal or the signal to noise ratio, there are different ways to measure it. And the way which I'm going to introduce, I think it's the most convenient one for most use cases. And it is something called CN0 or CN0, which means carrier to noise power measured in 1 hertz. There are other ways of measuring signal to noise ratio, but the issues with other ways is that when you speak about noise power, you always need to define how much bandwidth you use to measure the noise power, because since the noise is wide and it's present in all the frequencies, if you take a wider bandwidth to measure your noise power, then you will get a larger power measurement. So this CN0, what it does is to standardize the measurement by saying that noise power is always going to be measured in a bandwidth of 1 hertz, which is convenient for some of the calculations. So I'm going to begin explaining how this CN0 works by adding a variable. A variable is something that can contain a number or a formula. It's going to compute something either as a constant value here or a formula that depends on other values. And this n0 is the denominator. C n0 is actually like C divided by n0, and C means carrier power, which is like the power of the RF signal of interest, and then divided by n0, which means the noise power in 1 hertz. So this n0 is going to represent the noise power in 1 hertz. And then how should we calculate that? I'm actually going to do this more general and so that it matches what we have in the spectral analysis here. I'm going to define a variable for my noise amplitude. I'm going to set it as 1, but in this way, this will work for any noise amplitude. I could play and change the noise amplitude and everything would still work correctly. So, okay, you might remember that power is amplitude squared, so amplitude to the power 2. So the noise power is equal to noise amplitude to the power 2. However, what happens is this is the noise power in all my bandwidth. It is the noise power measured in a bandwidth of 1 megahertz because that is my sample rate. If I want to get the noise power in a bandwidth of 1 hertz, I need to divide by my bandwidth, which is the sample rate. So with this calculation, I get the noise power in 1 hertz. Then what else do I need to do? I need to compute the amplitude of this narrowband signal. And I'm going to define a variable. Actually, this should be a Qt GUI entry. So I'm going to copy it from here. This entry is going to be used to set our tone CN0. And then we have this thing. We want to add a variable, which is going to be tone amplitude. We will worry about the formula in a second. I'm going to set the tone amplitude here. So how should we compute the tone amplitude? Well, let's compute first the tone power because the amplitude is the square root of the power, as you already know. So what should be the power of this tone? And something important is that this CN0 is in decibels. Maybe I should write this thing clearly. So this is supposed to be in decibels. And then the first thing I need to do is to convert from decibels to linear units of power. And the formula to convert from decibels to linear units is you divide the value by 10 and then raise 10 to that power. The reason for that is just because the decibels are defined as 10 times the logarithm 10 of some number. And if you invert that calculation, this is what you end up with. So this is like the linear power of my tone CN0. But then this is supposed to be the quotient between the power of my signal and the noise power in 1 hertz. So this N0. So if this is the quotient and I want to compute power, what I need to do is this needs to be multiplied by N0. And this is the power that my tone must have. It's basically N0 multiplied by how many times larger than N0 this tone is supposed to be. That's what this CN0 actually means. For example, I think the example is quite illustrative. I have here 60 as the default. 60 is 1 million. If you do the calculation here, 60 divided by 10 is 6, and 10 to the power 6 is a million. So this means that my tone is going to be a million times more powerful than the noise in 1 hertz. So the power is 1 million times the power of the noise in 1 hertz. But that is the power. If what I want is the amplitude, I need a square root. And this can be computed with NumPy. They can be computed with the math square root function. I'm going to compute it with NumPy. And if I do it, I get an error which says NP is not defined, so this formula cannot be evaluated. The reason is I haven't imported the NumPy package. Because GNU Radio is wholly based on Python, there are import blocks here, which are like import statements in Python. And in Python, I would do import NumPy as MP if I want to use NumPy. And I can do the same in GNU Radio. I can do import NumPy as MP. And then I get this import block. It has successfully imported MP. And now this formula, which includes MP square root, works. And what we see essentially is that the amplitude of this tone for the default value of 60 is going to be 1. And the reason for that is if this has amplitude 1, then this will have power 1. And this thing has power 1 in a 1 megahertz bandwidth. So it has power 1 in 1 million hertz. And we have basically said that the tone by default is 1 million times more powerful than the noise in 1 hertz. So the tone ends up being um, the same power as the noise in my whole bandwidth, but this is just a coincidence because the sample rate happens to be 1 megahertz, and I happen to put here 60 dBs, which is the same as 1 million. So let's run this, and then I can stop for questions and also for the break. So we can see this is how a tone, which is 1 million times more powerful than the noise floor in 1 hertz, looks like. For example, let's try another value. If I put 40 here, that's 10,000 times more powerful than the noise in 1 hertz. So I can put it there, and we can still see the tone, but because there is noise, it is quite jumpy. So we need to use the FFT average to see the tone better. And you can see, for example, that this actually works. So now the value here is at minus 29. You shouldn't pay much attention to the absolute values that are here because they depend on how the FFT is scaled. But for relative measurements, they matter. So for example, the power is now minus 29. If I increase this by 10, I would expect to get minus 19. And once the average stops moving, I get minus 19 as expected. So that is the thing with this CN0, and these are very useful for measuring signal to noise ratios, because if you tell me I have a signal which has 50 dB CN0, I can already compare it mentally to other types of signals, figure out if it's strong or weak. If you tell me I have something with an SNR of, I don't know, 10 dBs, you need to explain to me which bandwidth you're using to measure the noise and so on. And it's like more dependent on your specific setup. Okay, questions about all of these. So far, we know how to generate the noise floor, and we also know how to generate one of these sinusoid signals, which essentially has zero bandwidth. It's concentrated on a single frequency. If we want to generate something more interesting, for example, if we want to think about communications in general, to communicate any data, we need to change some quantity about the signal. We need to modify the signal somehow. So this thing doesn't carry any information by itself. It's just, other than the fact that it's at a given frequency, it's not saying anything else. If we want to transmit some information with the signal, regardless of whether it's analog, digital, or any other thing we might think about, we need to modulate the signal. We need to change something about it. And because of how the mathematics work, changing something about the signal will always make its spectrum larger. It will not concentrate all the power of the signal into a single frequency. So wideband signals, that is signals which occupy a certain region of the spectrum, are also important. Essentially, any kind of communication signal is wideband. People draw distinctions depending on how wideband they are. Some of them could be just a few kilohertz wide. Some of them could be hundreds of megahertz wide, but they are all wideband in a sense. So the next thing I'm going to show is how to generate a certain type of wideband signals, because there are definitely many types of wideband signals. On the previous tutorial, we saw another type of wideband signal, which is FM radio stations. That is analog FM modulation with an audio signal on a radio frequency signal. But what I'm going to show now is something more abstract, which is band limited noise. What I want to do is to generate noise, but so that it only occupies a certain portion of the spectrum, not all the spectrum as we did here. And the way to do that in ground radio is somewhat tricky, but also easier. And I'm going to begin doing that by using a Gaussian noise source. And for the time being, the amplitude is going to be 1 because it will be easier to demonstrate like so. And if I do nothing, then I will get the same as here. I will get white noise that will be on all the spectrum. So the trick here is to invoke a fairly complicated block, but which is very useful for this. That's the reason why I'm including it on this tutorial, which is the polyphase arbitrary resampler. The thing that this block does is basically to change the sample rate without modifying any other properties of the signal as long as it's possible. And so, for example, if I generate noise, it's going to cover all my spectrum. But then if I increase the sample rate by, let's imagine a factor of 10, if, for example, if the bandwidth of this was 1 megahertz, if I increase my sample rate by a factor of 10, I end up with a bandwidth of 10 megahertz here. However, the noise on the input was only 1 megahertz bandwidth. So if this polyphase arbitrary resampler really wants to try not to change anything about the noise, it should preserve the fact that this noise source had a bandwidth of 1 megahertz. So what I would see at the output is I have my 10 megahertz of bandwidth, but only 1 megahertz is occupied by my noise source. So this is the way we are going to use this thing to generate noise which only occupies a portion of the spectrum. And I'm going to add some more entries, maybe copy them from here. So I have this wideband bandwidth, which is how much bandwidth the noise source in here is going to occupy. And I have this wideband bandwidth. And so the resampling rate, I was speaking about, if I increase my sample rate by a factor of 10, that 10 is the resampling rate by how much we increase our sampling rate. We can also decrease it if we want, but for this application, we always want to increase it. And the factor by which we want to increase it is my sample rate, which is 1 megasample per second in this example, divided by, how did I call the entry, wideband bandwidth? Wideband bandwidth. So this is 6.666, which is basically 1 megahertz divided by 150 kilohertz. That's the noise in here. The bandwidth needs to be expanded by a factor 6.66 to fill up the whole 1 megasample per second bandwidth that we have. And this might seem confusing. The remaining parameters are how to compute the filters for this resampling operation. The defaults are more often than not very good values, so you can just leave them as they are, unless you are doing something really, really special. And now to see how this looks like, I can perhaps use the average so that we can see it better. We have our noise, which is limited to 150 kilohertz bandwidth. We can see it goes from minus, I don't know, minus 75 kilohertz to plus 75 kilohertz. It doesn't decrease completely vertically. There is a certain slope. We can maybe see that better if we zoom in. So it goes down with a certain slope, and that's because the filters used here. So no filter can be ideal and go immediately from one value to another. They are always smooth like that. They always have skirts. This is called the filter skirt. But that's basically what we wanted to do. We can generate a chunk of noise, which we can even choose how large it is. So we can make it 300 kilohertz wide, for example. And then once the average stops, we can see that now this thing is larger. And if I make it larger, for example, 500K, you can see it's larger. You might also have seen that it's going down in the spectrum. I can easily do a comparison with 50 kilohertz. You can see it's narrower, but it's more powerful. It goes up. And the reason for that is the total power of the noise is the same always. It's given by the amplitude, which is fixed to 1 at the moment. But because we are changing the bandwidth and then power is distributed over all the bandwidth which is occupied, if the noise is narrower, then we distribute the power over a smaller bandwidth. So basically, everywhere here, we get more power or power density, if you wish. This is just because constant power, but the thing which the FFT is plotting is not power, it's power spectral density, is how much power over frequency we have. So that's also something to keep in mind. Just because you see that some signal is like really tiny here, it doesn't mean that it's necessarily weak. If it's wideband, then you need to integrate all the power across the bandwidth of the signal. So, okay, that's how we can generate this noise. Maybe we want to put it somewhere else because for the tone, we have this tone frequency and we can choose where to place it. How do we do that for the um, wideband signal? And there is a way to do it, which is we essentially know how we saw it here. So it's with this multiply conjugate with a signal source. And that's what I'm going to build in here. I think that's what I have on the original flow graph. Yep, that's the same. So multiply, and in this case, it's multiply rather than multiply conjugate, the operation, which is more natural because I can go multiply, I can then go signal source, I can grab this and say wideband frequency. This needs to have an amplitude of 1 for sure to preserve the amplitude of the thing I'm multiplying it with. And then I can copy my tone, sorry, not tone frequency, but rather wideband frequency from the other to avoid some typing. And this is set to a default of minus 300 kilohertz. So now you will see that the noise chunk is no longer centered at 0. Now it's centered at minus 300, as you can see here. So the center is about here, minus 300 kilohertz or minus 0.3 megahertz. So now you know how to generate both narrowband signals like this one, wideband signals like this one, how to place them wherever you want in the spectrum. You could keep generating more and more of these signals and adding them together. And with these tools, you can generate a fairly complex scenario of signals. Something else which is important is we haven't adjusted the power of the noise here. So how do we do that? We also want to do that in terms of CN0. So in fact, I have my wideband CN0, which is also 60. That means that the tone and the wideband signal will have the same power by default. So how do I set the amplitude? Wideband amplitude. And essentially, I need to do a calculation, which is going to be the same as here for the same reason, actually, but with wideband CN0 rather than tone CN0. And now we can set the wideband amplitude here. So that's how it works. And I can set the average to high. And now, because of the way we have set the values, we have 60 dB on both of them. So this tone and this wideband signal have the same power. And it doesn't seem like so on the FFT, on the spectrum. And the reason for that is, well, the spectrum is not a great tool to see the power of signals directly. We can see how much power is at each frequency, but to compare the power of this thing, which is extended in frequency, with the power of this thing directly, requires some calculations. Basically, we need to add all the power in here and then compare about with the power in here, which is concentrated at a pretty much at a single point, as we will see later on. Okay. Any questions about this? Great. The next thing I want to worry about is what happens with weaker signals. Can we detect them? Do they reach a point in which they are too weak and we can no longer detect them? Can we do anything about it? And we will see. And the answer is that these frequency sync in ground radio is useful because it's easy to use, but it's not the most sensitive spectrum plot that one can do. And so we will make our better plot from scratch. So I can begin by playing with the wideband signal. And for example, if I make it 30, we cannot see anything. What happens if I make it 35? I don't think we can see it. 40, what about 40? Uh, Maybe not. 45. Maybe it's actually there. Like maybe you see that there is something slightly above the noise floor, but I think we need to go closer to 50 to be able to see that. Yeah, at 50 we can clearly see it. So the threshold at which we can detect this signal is between 45 and 50 dB CN0. And I haven't said it, but why so important to think about when we can detect a signal, how strong it needs to be, can we do anything with our processing to be more sensitive and detect weaker signals? Well, that is very relevant for SETI because we think that SETI candidates are going to be weak because they come from very far, and because otherwise probably we would have found them already. If there is a SETI candidate which is very strong, everyone would see it with any kind of radio, right? So if we haven't found them yet, then it means that they are weak if they exist. So we need to use large telescopes, but also good signal processing to be as sensitive as we can. So that's why I'm stressing these notions about signal detection in the spectrum. So okay, that's what happens for the wideband thing. With this kind of processing, it can be detected. I don't know, maybe let's call it 47. Uh, then what happens with the tone? I think if I go to 40, we can still see it fairly well. Yes, let me try with 30. Probably we can see it still. Yes, so maybe I need to go to something like 25 to lose it. Yeah, I think 25 already disappears. So maybe, I don't know, something like 27, perhaps even 28 is what we need to see it. I think we see it now, but sometimes it's like almost disappearing. So, well, something we have seen is that the tone can be detected with much less power, 27 decibels compared to 47 decibels. And the reason for that is just the occupied bandwidth. It is much easier to detect narrow band signals because they only occupy a very thin portion of the spectrum, and we can see the signal, all the power is concentrated there. Whereas these wideband signals, the power is spread over a large portion of the spectrum, and we cannot do anything smarter to detect them unless we know additional characteristics of the signal. But the question is, can we do any better? And the answer is yes. The reason why the answer is yes is that the average which is done here is not very good. It is an exponential average. which is okay, but there are better ways of doing averages. And we only have these controls like high, medium, low, and the high is probably not high enough. So how can we make something like this plot, but from scratch, so that we can understand how it works and we can improve it? Well, that's not too difficult, and that's what I'm going to show next. So I'm going to begin by introducing another block, or actually pair of blocks, which are the virtual sink and virtual source. These blocks are like a virtual connection. So what happens is that anything I connect here will uh, be output there. This is like running a line directly between these two. And the only reason why this block exists is because it allows you to make flow graphs tidier. For example, I can put this one here and begin putting blocks there. And the other way of doing so would be to run a line from here to here, but it would be crossing there. And you can imagine if we make a more complex flow graph, it will be a mess. So that's why we have virtual sink and source. And there is an ID, which is any name, and it needs to match here. So signal, signal. That means anything that goes inside will come outside in there. I want to use an FFT because computing the spectrum requires an FFT always. To use an FFT, I need to define the FFT size, which I'm going to call NFFT, as in number of FFT points. I'm going to use 4096, which is the same number I'm using here. And then you can see, you might notice this is dark blue and this is a lighter blue. If I try to connect them together, I get an error. For sure, I actually need to put NFFT here. And there's a window, which I also need to set the size of the window. And I will come back later to what the window is and why it is useful. Uh, but my point now is that I get an error. And why is that? It has to do with the slightly different colors. If I click in here, it says port is not connected. This is about the output of the FFT. Well, I know that already. But the second message is source IO size 8 does not match sink IO size 32768. And the reason for this is the FFT operates on vectors. The FFT needs a whole vector of 4096 points before being able to do anything. Whereas these other blocks, they operate sample by sample. So what we need to do is to take our samples and package them as a vector. And there is a block to do that, which is called stream to vector. So whenever you are dealing with FFTs, you will be converting back and forth from vectors to streams quite often. The only parameter that this takes is the number of items, which is NFFT, how many items to put into the vector. There is another parameter which is called vector length. Maybe this is slightly confusing. I don't know how it's explained in the documentation, probably not so clearly. This is for the case when we want to make a vector of vectors. So we could have vectors already of, I don't know, size 10, and we would make a vector of 20 of those 10 value vectors. And so we would have vectors of size 200. That's the reason. So it's like input vector length. Probably putting input here would be really helpful. In our case, we begin with not with vectors, rather with individual samples. So the vector length is 1. So, and this is the most common use of the block. So that means most of the time you do not need to set the vector length to anything different than 1. So now this connection works because we have used stream to vector. And now what do we need to do? Well, the first thing is that the FFT outputs complex numbers because these complex numbers contain both the power of the signal in the modulus of the signal, but also the phase of the signal in the angle of these complex numbers. I only want the power. So there is a block which is called complex to magnitude squared. It is the modulus squared of the complex number, and that is the power of the complex number. So I can set this thing and set it to a vector length of 4096. Many blocks in GNU Radio support vectors, but you need to set manually the vector length. So by doing this, I'm computing the FFT, then I'm converting to power, which is a vector of real numbers. The next thing I want to do is to integrate, which is basically to sum a whole bunch of FFTs. By doing that, we are essentially averaging, and by doing an average, we decrease the noise. So that is what will make this FFT processing more sensitive. So let's take a look at the integrate block. I'm going to connect them, yeah, but I need to set some properties for the connection to work. So first, the type. I want to integrate real numbers or floating point numbers, not complex numbers. Then the decimation, which I'm going to set with a variable. I'm just going to call it integration. And then the vector length is NFFT. So this is going to sum integration. Let's pretend for a moment that integration is 7. So this will sum 7 vectors together, component by component. So the mathematical vector addition, and then it will produce an output. So for every 7 FFTs I compute in here, I will get an output. We are decreasing the output rate essentially by a factor of 7 or by a factor of integration. But because we are adding together all these FFTs, we are reducing the noise, as we will see. So how can I set my integration? I'm also going to copy this. Maybe it was also called integration. Oh no, it's a variable actually. So I have this T integration, which is the integration time in seconds. I actually don't like T int so much. I'm going to call it integration time seconds. So I want to generate a measurement, so a single spectrum plot every 1 second. I can change this later on and make it, I don't know, 10 seconds, 0.1 seconds, or whatever we want. The longer the integration time, the more sensitive the plot will be because the more noise averaging it will perform. However, we need to wait more. For example, we could do a 1,000-second integration, and for making astronomical measurements of weak astronomical sources, that is not unheard of. It is sometimes common to use such long integration times, but we need to wait for 1,000 seconds before even seeing anything. So we are not going to do that today. You can try that later on, and because this is a simulation, you can increase the sample rate and achieve the same results way faster. So integration time 1 second, just for the time being. And then I have another variable, which is going to be the integration. So how many of these FFTs I need to sum to get 1 second of integration? Well, my sample rate is 1 megasample per second. It is here. That means I have 1 million samples per second. Then the next question is how many FFTs per second are we doing? Each FFT is using 4,096 points. So the number of FFTs per second is this thing, the sample rate divided by the number of FFT points, which is 4,096. If I want to integrate integration time seconds, then the number of FFTs within that time is the number of FFTs per second multiplied by integration time second. And this number is probably not an integer, it's 244 point something. So it is true that we cannot make our integration time exactly 1 second, but we can round and we will get 244 FFTs. So this thing will be summing up 244 consecutive FFTs, producing an output, then take the next 244 FFTs, produce another output, and so on and so forth. The next thing is most spectrum plots are in decibel units because they allow us to see simultaneously both strong signals and weak signals. So to compute or to convert these to decibels, we need this logarithm 10 thing. And we need to set the n to 10. This is like 10 logarithm 10. So the n is the 10 in front of the logarithm 10. If that makes any sense. Maybe here it's in better. So 10 times, that is why n is 10, logarithm 10 of input, We can optionally add a constant k. We don't need that today. So that's how we convert to dBs. And then what else? The vector length, as always, NF50. Finally, we need a plot, a block to plot this output. I'm going to copy it from here because I don't want to type all the settings manually, but I will explain them. Because this is a vector, the way to plot it is the vector sync. This will plot a vector at a time. So we will see like 4,096 points of the spectrum. We set the vector size and then the x-axis. These are the numbers I didn't want to plot, sorry, to type. This is my frequency scale. So if I want my frequency scale to be correct, my start needs to be minus the sample rate divided by 2. That's my lower edge of frequency. Remember that the frequency range goes from minus sample rate divided by 2 to plus sample rate divided by 2. And then the step is how much increment in frequency I have for each of my 4,096 points. Well, the step is sample rate, which is the whole bandwidth we cover, divided by NF50, which is how many points we have. And I think the remaining values are default. So the only thing which you need to remember here is how to set the scale for the frequency. And I think that's it. So let's use this, and maybe I need to auto scale because otherwise we don't see anything. Oh yeah, I see what I'm missing. Probably I have a repeat block. Yes. So this is a trick. The problem here is that this is producing only one vector per second, which is fine. That is what we want to have here. We want this to update once per second. But the problem is GNU Radio usually has buffers in the block connections, and for performance, it will normally wait for certain numbers of outputs to be produced here before even doing something. So that means we need to wait for many seconds. And that's the reason why when I was running this, we don't see anything here. So the trick, it's a very simple but not obvious trick, is to use this repeat block, which does what its name says. It repeats every input as many times as we say, and I'm going to repeat every vector 100 times. And the vector size needs to be NF50 and the type needs to be float. Then what happens is this block produces a measurement every second. The measurement is converted to decibels. The measurement arrives here. It's repeated 100 times. So we get 100 vectors with the same contents. This thing now has enough inputs to begin working. It will basically plot the 100 vectors on top of each other, overwriting it. We will not see it because it's like very fast. And it's also the same value. So there is nothing to see. We are like plotting 100 times the same value on top of each other. And then it will wait until the next second when the next value is produced, and it will repeat 100 times more, and this will refresh. So that's the trick to get this refreshing. So now you can see every second, like plum, plum, this is updating. And oh yeah, it looks much nicer than the default GNU radio frequency GUI sync, even if I add like this high average. You can see that the noise is lower here. That wholly depends on our integration length. I can, for the sake of the example, set it to, for example, 5 seconds. And we now wait 5 seconds. I can set this again to high. And you can see, so it's going to take 5 seconds to update, but the noise floor is highly reduced. Because 5 seconds is a lot for interactive testing, I'm going to set it back to 1 second. And now we can compare the performance of weak signal detection of these two plots. So let's see, high. And we can go to the values we had before, which I think were 47 and 28. So I think this will disappear. It's still there because of the average, but eventually it will disappear. Maybe I can try to zoom in more. I can try to zoom in more in this one. And what do you see? Well, with 28, it's still there, but I don't know, 26, it's gone in here. Maybe it appears occasionally, but in here it remains. And this one is like a fresh refresh every second. So every second I'm getting a new measurement. And if I change a value here, I need to wait just 1 second to see the outcome. In this one, it's like an exponential average, so things decay over time. Uh, but you can see this processing is way better. So this can be seen more clearly. I guess if I set this to 46, then it will be much more difficult to see in here. And in here, we can still detect it very easily. And in here, we can see it very easily. So that's my recommendation. Whenever you are dealing with something which is weak signal detection, do your own um, FFT processing in this way, because then you can tweak all the parameters. You can tweak the decimation. You can tweak the FFT size. Well, the FFT size you can also tweak here, but you have more control and you know exactly what's going on under the hood. So questions?
I just had a comment about this for those that are sort of using radio spectral data from the GBT or from other telescopes that particularly with the GBT, you're probably familiar, there are different data products. So there's a fine resolution product, there's a mid resolution product, there's a coarse resolution product. And essentially you just make a choice on what that FFT size will be, which then determines what your frequency and time resolution will be. And then there's that averaging step. And so sort of natively you could choose 1 hertz 1 second, which is sort of set by the limits of the sampling and the uncertainty principle, or you could choose 3 hertz, which will give you 1/3 of a second resolution. But our 3 hertz data product at GBT actually has 18-second time resolution because we accumulate those samples. We accumulate, I think, 53 samples to get 3 hertz, but then 18-second time resolution. So it's poorer time resolution, but it also makes the files more manageable in size as well. The downside of that is if you look at this, the narrowband signal here on Daniel's plot, if that narrowband signal wasn't constant in frequency, but it's drifting due to the Doppler effect, for example, over time, if it drifts more than one channel in the course of one integration, then it's going to get smeared basically and you lose power because it kind of turns into something that looks more like the broadband signal on the left there. So these choices of sort of how long you want your FFT to be, how long you want your integrations to be, and then sort of what that gives you in terms of your ability to detect a Doppler drifting signal in particular, one that's changing with some rate of frequency per time bin is very sensitive. And that's in part, that's why we have these different data products, because it's the same underlying data, but then for different applications, you might want different combinations of time and frequency resolution, if that makes sense. Any other questions for Daniel?
Okay, so the next thing I'm going to show related to what Steve was mentioning is to show you how the FFT size that we use influences our detection capabilities, especially for this narrowband signal. We have been using 4096, and a question you can ask yourself is why these values? What sets how weak of a signal we can detect? And for narrowband signals, the calculation is fairly easy, at least to get a rule of thumb that will give you an approximation. And the way to think about it is in terms of the FFT bin width. So that's how much bandwidth each of the FFT points has. For that, I'm going to use Python as a calculator. I could also use, again, a radio variable, but I think it's easier this way. So my full bandwidth is 1 megahertz. This is what I have here. And my FFT size at the moment is 4096. So that means that each of the FFT bins is 244 point something hertz. So the noise power I have, maybe it's useful to zoom in here. and enable these markers so we can see the individual points. The noise power that I have on all these points, which are only noise floor, is the noise power in 244 hertz. And then the question is how much, I need to import NumPy, how much is that in decibels? It's going to be about 23. So 23.8 something. This means that if my signal were to have a CN0 of 23.9, let's call it, so 23.9, then this signal is going to have the same power as each of the noise bins. And that is the rule of thumb. If it has about the same power or more power than one noise bin, we will be able to see it because it is so the signal itself is concentrated on about one or two FFT bins. Next, we will see exactly what determines that, and and then if it has like a power which is comparable to the noise power in those bins, we will be able to see it. For example, if it's the same power, we expect a 3 dB increase, which is that is like multiplying the total power by 2, which is something that we can see. But if it has something much smaller, like I don't know, for example, 20, we will just lose it. So that is the rule of thumb. That is how the FFT size plays out. I could do an example of changing the FFT size to, I don't know, 8 times larger or something like that, and then showing that we can actually detect a signal of 20 dBs because the bins have become narrower. In the interest of time, I will not do the example. You can do it yourselves later. It's very easy. Just change the FFT size and play with it, see what happens. The other thing I'm going to do, which is also interesting and important, is to look at the at what happens with narrowband signals. Where do they end up in the spectrum? For that, I think it's actually easier to, well, I can begin with the signal. It's at a frequency of 10,000 hertz, so 100 kilohertz. And you can see the signal is fairly strong. We can forget about the noise. There's signal power in all these 4 bins. The reason for that, there are a couple of reasons for that. The first reason is that this signal is like halfway between 2 of the FFT bins. You can see that by the fact that the power is almost like distributed equally between these 2 points. No wonder, because if I do 100 hertz divided by this number, what I get is that my signal is going to be at being centered on being 409.6. So that's almost halfway between 2 bins. So bins 409 and 408 will get most of the signal power. And then these 2 adjacent signals also get power. To demonstrate this more easily, I'm change where my signal is. I'm going to put it at 0 because then it will be easier to see. So when the signal is at 0, what happens is I get a peak directly at 0. Then the next bins are like are the same power, each of them. So that means the signal is well centered in this bin, and then it goes like this and that. And something I want to take note of is what is the power here. So it's about 67.5. If I keep increasing my tone frequency, for example, 50, I'm basically moving my tone to the right. I cannot see it moving 50 hertz because my frequency resolution is 144. Sorry, it's 200 and what was that? 244. So that means that the a smaller movement of 50 hertz, I can only see it by the power being redistributed. And now this thing is lower, this thing is slightly higher. And I can continue. If I do 122, then it's going to be about halfway between now being 0 and being 1. And what happens is the power is now lower. So it's 66.6, more or less. Remember that it was 67.5. So we have lost pretty much zero point 0.9 dBs because our signal happens to be halfway between two bins. That was 122 to get it exactly halfway. That's kind of bad luck, since in principle we don't control the frequency of the signals we will be receiving, but it's something that can happen, and sometimes you need to prepare for the worst case. The reason why we have less power on this is because the power has been distributed. The total power needs to stay the same. That is a property of the Fourier transform. But if now the signal is halfway between the bins, it needs to be distributed between these two. So this effect is called scalloping losses. If you hear about scalloping losses, that is the thing we are talking about. And the thing which determines how large the scalloping losses we have, and also something else which is called spectral leakage, is the FFT window. So what's spectral leakage? Well, you can notice that the signal is not on a single bin, not even when it's completely aligned here. It also spreads to a couple bins to the sides. That's spectral leakage. The signal is supposed to be here, but we also see it in those bins. And the window defines these two. Basically, we can optimize for spectral leakage. So we can optimize for reducing the spectral leakage. We can optimize for reducing the scalloping losses. We can optimize for a combination of them, but there is always a trade-off. We cannot improve on both things simultaneously. So that is the reason why there's a window, and there are many windows that people can choose from, depending on what they are after. So the most basic window is a rectangular window. The window is, by the way, a vector of 4096 numbers. It's nothing magical. So the rectangular window is a vector of all ones, or in this case, it has been scaled by dividing it by whatever number to preserve power. So that's the most basic, and the reason no one uses it is that it is excellent when the signal is, sorry, I wanted to put 0 first and then show markers. So the rectangular window is excellent when the signal is centered exactly at an FFT bin, because then we only see the signal at that FFT bin. Since the power is only concentrated here, there are literally 0 scalloping losses. So for this case, it's the best choice. But that case is like, you need to be very lucky. If I ever shift my thing by 50 hertz, now you can see the spectral leakage is huge. I see my signal distributed over all of these points, and that for sure causes a lot of scalloping losses. And you can see with 144, I think there are 3 dB of, sorry, that was 122 to get it halfway. I think there are 3 dB of scalloping losses. I'm not going to measure it because I want to get done with this thing since before the top of the hour, but you can believe me. So in some cases, you want to optimize for these scalloping losses, and there is something which is called a flat top window that is, for example, used in spectrum analyzers. Because in a spectrum analyzer, you want to measure things like accurately, and you don't want to have some losses just because your signal happened to be in between two bins. So I can show you that this window has pretty much no scalloping losses. That is basically how the window is constructed. You ask yourself which vector of numbers would give me pretty much no scalloping losses, and then you end up with that definition of a window. So when the signal is centered at 0, it's centered on this bin. We can see the power is 82. It's not the same power as before, and that's what I told you. Do not make much use of these absolute numbers. They are only good relative. If you want to make use of them as absolute values, you need to understand exactly how the window scales things, how the FFT is scaling things, and oftentimes it's not necessary to go through that. But anyway, this is 82.7. You can see it has poorer spectral leakage. So now it's like these have very large values, and it has like 1, 2, 3, 4, 5, like 9 points or something that it's occupying. If I shift my signal by 50, you can see it's still flat. It's at the same 82 point something. If I shift it halfway to 1 to 2, you can see it continues being flat. That is the reason why it's called flat top. And it has basically no scalloping losses. And that means that regardless of where the signal is, uh, we are um, we are not going to have losses if we get unlucky on the frequency alignment. The downside is more spectral leakage, which means we are throwing away signal power, so you can get everything you want. You can do processing with multiple windows and examine the results separately. That's always a strategy. Um, so I think that's it for today, pretty much. Any questions?